Hello, everyone, and welcome to week 4. In this week, we will continue our discussions of Chapter 3 Vector Valued Functions. Last week, we introduced section 3.1 in Chapter 3, the first section of Chapter 3. And we plotted vector functions, we introduced vector functions, and we talked about uh, their limits and continuity. In this week, we will cover 3 sections. Today, we will discuss section 3.2, the calculus of vector-valued functions. We will discuss the derivatives and the antiderivatives of vector functions. Let's write, first of all, the derivative of a vector-valued function. The derivative of r, where r is a vector function, is written as r prime of t equal to limit as delta t tends to 0. And we subtract r, the vector function, from r of t plus delta t, where delta t is the increment, as you approach your limit. And this increment decreases as you approach your uh, your the limit you're interested in. And this increment, of course, approaches 0, which means that the increment uh, is getting smaller and smaller as you approach your limit. And you divide this by your increment delta t. We will talk about the derivative in the next slide. Now we're just writing the definition. We say that r prime, the derivative of the vector function r, exists, which means that if you calculate the limit or you calculate the derivative and you don't encounter um, undefined results, in other words, that your derivative exists, then the derivative r is differentiable at t. So we say r is differentiable at t. For a function is differentiable over an open interval a and b, this is an open interval. As you can see, we're using parentheses, which means that a and b are excluded. If the vector function is differentiable between a and b, this means it is differentiable over all the points between a and b, excluding a and b. If the function is differentiable over a closed interval a and b, now we're using square brackets to indicate that a and b are included. So in this case, our definition, we'll make a small adjustment in our definition. So the derivative of r, which is denoted by r prime at a, is written as the limit as delta t tends to 0 plus, which means that you're approaching a from the right. 0 plus means that we're approaching your limit, which is a in this case, from the right. Delta t again is the increment, which means this increment is getting closer, smaller and smaller, smaller and smaller, approaching 0, which means that you're approaching a, and your increment with respect to a, the distance between you and a, is becoming smaller and smaller. And the plus over here, the subscript, the superscript of 0 shows a plus sign, which means you're approaching from the right. The same definition as above, but you replace a in t. This is called a right-hand derivative, which means that you're approaching 8 from the right. As you approach the upper limit b, we will say that the derivative of r of b is equal to the limit as delta t tends to 0 minus to indicate that you're approaching b from the left and you're getting closer and closer to b. Your increment is getting smaller and smaller, and we write this as a minus in the superscript of 0. And this is called a left hand derivative. I've prepared a few additional slides about the derivative to recall some basic ideas before proceeding. Let's start with this simplest type of function, which is a straight line, and this is written as y equal to f of x equal to mx plus b. M is the slope of this function of the straight line, and b is the y-intercept. Now, we consider 2 points. Uh, the first point has coordinates x1 and y1, and the second point is over here and has coordinates x2 and y2. To calculate the slope of this straight line, we calculate the rise over the run. To find the rise, y2, the rise is equal to y2 minus y1, which is the distance between y2 and y1, this one over here. If you calculate y2 minus y1, this will give you the rise, the distance from here to here, divided by the run, which is x2 minus x1. x2 minus x1 is this one. This one is the run, and you have this formula for the slope, y2 minus y1 divided by x2 minus x1. Or it can be written as the slope equal to, instead of writing y2, we're gonna write it as f of x2 minus y1 can be written as f of x1. So the slope is f of x2 minus f of x1 divided by x2 minus x1. Let's extend this idea to a function uh, which is a non-linear function. Consider this function having the form like this. Now, we will also consider 2 points. This is the first point, and this is the second point. The first point has the coordinates of x1, f of x1. So this is y1. And the second point has coordinates of x2 and f of x2, and f of x2 is y2. Now, to calculate the rise over the run, this is the same formula as before, but this time you're calculating the average or the rate of change between these points. If you take different points on the function, you will get different rate of change. And if you connect these points together between the first and the second point, you will get a, a line, we call it a segment or a secant segment. This is the secant. And this calculating the rate of change will give you the slope of the secant, because this is the same formula, and calculating the slope between 2 points will give you the slope of the straight line. So this is similar to this case. If we calculate the rise of the over the run between these 2 points, you will get the slope of this line, which means the slope of this secant. Now, as the curve changes, the average of change will change between these 2 points. Of course, if you have a function with a different form like this, and you take another point over here, and you connect them, you connect these 2 points to get the secant, and you calculate the slope, the rise over the run, you will find a different, you will calculate a different slope, because this is a different secant segment, which gives you a different slope, which means that you will get a different average of change or rate of change between different types of functions. Now we will change the notation a little bit. Instead of using y1, y2, x1, and x2, for the first point, the coordinates will be x and f of x instead of x1 and x2. And for the second point, instead of writing x1, x2 and y2, we will write the second, the abscissa of the second point, this one, instead of x2, we will write it as x plus h. So it's the same amount of x, and adding some value to 8, we will call it h. So x plus this added value to x, which is h, this will be the abscissa of the second point, which is this one, x plus h. Now, the same thing goes to the y. We will write f of x plus h. Now, this formula will looks like the slope of this secant line, which we were writing it as such over here. Now, x2, f of x2 will now be written as, this was x2, will be written as x plus h minus f of x1. X1, now we have it as x, divided by x2 minus x1. So x2 is this one, minus x1. X minus x will cancel, and we will get h in the denominator. So this formula, you can see that this formula looks like something we already know. As h gets smaller, this the distance between this increment I was talking about in the first slide of this presentation. This increment delta t or h, or call it whatever you like, this the distance between the 2 points. If the distance between the 2 points decreases and decreases and is getting closer to each other, the formula can be written as the limit as h tends to 0. The distance between the 2 points is getting smaller and smaller. What's gonna happen? Compare the two figures, and the second point is getting closer to the first point, and this distance is getting smaller, which means that h is tending to 0. At some point, the 2 points will become very, very, very close to each other, and you have something like a single point. This is the limit, and we're approaching each other, never touching each other, but they will look like as if it is a single point. At this, in this case, you no longer have a secant line like here and here in the first figure over here. You will have a single point, and this secant line will be called a tangent line, and this is the point of tangency. The point of tangency is given by the first point, x and f of x. So since no 2 points exist to find the average rate now in this case, instead of average rate, we will call it the instantaneous rate of change, which means that the rate of change at this instant, at this particular point. So this limit over here, it's called also the derivative in mathematics, and we will call it, denote it by f prime of x. And it will give you the slope, Now, instead of having the slope of the secant line, you will have the slope of a tangent line at this particular point. In mathematics, we call it derivative. In physics, we call it the velocity. The velocity, which means that the rate of change at this particular point, the velocity of this function at this particular point in physics and mathematics, it is the rate of change at this particular point, or it is called the derivative. This is an example about having a slope, calculating the slope of a tangent of this function f of x squared at point minus 1, 1. Again, we can use this equation for the derivative. So we want to do the derivative of the function and then replace it in the function, replace this point in the function. You have start uh, with the first part of the first term in the numerator and replace x plus h in x squared. You will have x plus h, all of that squared, minus f of x, which is minus x squared divided by h. Expand x plus h, all of that squared. You will get x squared plus 2hx plus h squared, and we have minus x squared. So now we can cancel x squared and minus x squared. You will have something like that, and we can factor out h. Factor out h, and then you can cancel it with the denominator over here, and you will get 2x plus h. Now let's find the limit of 2x plus h. This one will be 0 because h is tending to 0, and the result is equal to 2x. 2x is the derivative of this function, which is equal to x squared. Now let's replace the point x is equal to 1. Replace 1, this should be minus 1. This should be minus 1. Replace minus 1 in the derivative, and you will get minus 2. Minus 2 is the slope of this tangent line at this particular point. Okay, let's continue. Okay, let's continue our lecture after recalling basic ideas of the derivative. Many of the rules for calculating derivatives for real functions can be applied to calculating the derivative of vector values function. So the rules you are using, you used to use when you apply the derivative to real functions, real valued function, is similar to the derivatives of vector valued function with a few modifications, with new rules. We will discuss them now. The derivative of a vector valued function can be understood to be an instantaneous rate of change, as we saw in the previous slide, in slide number 6, that the derivative the derivative at a single point will give you the instantaneous rate of change. This is the derivative of a vector function will give you the instantaneous rate of change. The derivative at a particular point will give you the slope of the tangent. Now, for example, when we have a function that represents the position of an object at a given point in time, the derivative represents the velocity at that point in time. As we said, this is called velocity in physics, and the derivative of a vector function will give you the velocity vector at this particular point in time. In example 3.4, we will use the definition we introduced to calculate the derivative of the function. We have a vector function with x and y components, which means this is a two-dimensional vector function. So let's apply our definition. We will replace t plus delta t. We will replace plus delta t in the vector function, and you replace it in every t in the vector functions, in t squared, and t over here. So let's do that. We replace t plus delta t. In t squared, we replace it here, and in minus 4t, we replace it over here. This is r of t, and this is r of t. This is r of t plus delta t. Okay, so we expand 3 times t is 3t, and 3 times delta t is 3 delta t. Now, this is multiplied by the I unit vector, and we also have minus 3t plus 4. This comes from here. This comes from here. And we will combine j together now. Expand t plus delta t will give you this one over here, and minus 4 times t is minus 4t, and minus 4 times delta t is minus 4 delta t. Okay, now let's subtract these. We have 3t and minus 3t will cancel, and plus 4 and minus 4 will cancel. We will only have 3 delta t times I. And for the j, you also subtract, and you'll get the subtraction of t and t squared, 3, and over here we have 3 minus 3, and 40. Minus 40 plus 40, because minus times minus is positive. We will only have in j 2t delta t plus delta t squared minus 4 delta t. Okay, now we can factor out delta t, where you will cancel the delta t's together, and we will have one delta t over here, which is this one. Find the limit as delta t tends to 0. This one will be 0, and you will get 3i plus 2t minus 4j. Okay, so this is the derivative of the vector function r. Let f, g, and h be differentiable functions of t. If you have, these are real valued function, which f is the x component of this vector function, and g is the y component of this vector function. This is a vector function in 2D. Then the derivative of r is the derivative of each component alone. You do the derivative of each component individually. So the derivative of r is the derivative of f, and the derivative of g prime, which is the y component of j. In 3D, this is the same. You do each component individually. We have a third component, which is h. You do the derivative of h, which is the z component of this vector function. Let's consider an example. Let's calculate the derivative. We have 3 vector functions. R is, let's start with the part A, and we want to calculate the derivative of this vector function. Of course, the derivative of each of this vector function is the derivative of the x component plus the derivative of the y component of this vector functions. Let's do this each one alone, and then we're gonna add them. The derivative of 60 plus 8 is 6, and the derivative of the y component is the derivative of 4t squared is 80, and the derivative of 2t is t, and the derivative of 3, which is a constant, is equal to 0. Now let's add these together. We will have 6i plus g prime is 80 plus 2j. This is the derivative of r. For the second part B, we have this vector function. also a two-dimensional vector function. Let's start with the x component, which is 3 cosine t. The derivative of 3 cosine t is minus 3 sine t, because the derivative of cosine t is minus sine t. For the y component, we have 4 sine t. Let's do the derivative of 4 sine t. The derivative of sine is cosine t. Add them, we have the x component, the derivative of the x component, which is minus 3 sine t, and the derivative of the y component of r is 4 cosine tj. The third part is a three-dimensional vector function, and we have all three components. So we will do the derivative for each one alone, and then we add them at the end. The derivative of et sine t, we will say that let the first one be u, the, and the second factor be v. So the derivative of, let's recall this idea, the derivative of u times v is equal to u prime v plus v prime u, which means we do the derivative of u, then we multiply it by v plus now the derivative of v times u. Let's do that. The derivative, let's apply this formula. We start with the derivative of u. The derivative of u, the derivative of et is e to the power of t times v. We don't do anything for v, we just write it, is sine t, plus, now let's do this one. We do the derivative of v. The derivative of v, the derivative of sine t is cosine t times u. U is, in this case, we don't do anything for u, just write it again. It is e to the power of t. We can factor out et, take it common, and we will have sine t plus cosine t. Similar thing we will do for the y component, which is e to the power of t times cosine t. Do it, apply this formula, and you will get e to the power of t cosine t minus sine t. And for the y is z component, this one is minus e to the power of 2t. The derivative is minus 2 e to the power of et. Now replace them or add them, the three together. This one is the x component of the derivative, this is the y component of the derivative, and this is the z component of the derivative. So this one is the derivative of r.